We are looking at shortest paths in weighted graphs, and we said there are two types of shortest paths, single source and all pairs. So let's look at single source shortest paths. So we want to find the shortest path from a fixed vertex to every other vertex in a weighted graph where we have this weight function which assigns a real number weight to every edge. And for now, we will assume that these weights are all non-negative, right? So there are no negative weights in the graph. So the shortest path problem now is to compute the shortest path from some fixed vertex. So let us say that fixed vertex happens to be 0. Okay. So we want to compute the shortest path from 0 to every other vertex. So here is a way to think about it. You think about the time it will take to reach every other vertex from 0. So you start off some process which takes a uniform time according to the cost of the path, right? So you can imagine that if these are roads that you are walking on, and these paths are these weights are actually lengths of roads, and if you walk at a uniform pace, then the time it will take you to reach a given place will be proportional to the length of the road up to that place, right? So to graphically illustrate that, let's assume that these are oil depots and these edges are actually oil pipelines, right? And now we set fire to this depot at vertex 0. So the fire will now travel along all the pipelines at some uniform rate in all directions. So you wait to see where this fire will reach first, and that will set fire to the next depot. So for instance, if the fire travels at a uniform speed, the first oil depot to catch fire after 0 is going to be 1, because if I start a fire from 0 and go in both directions, then after 10 units of time the fire is going to reach vertex 1. Then if the fire continues to flow, then the fire will propagate from here in both these directions, and then the next vertex to burn will be the one which is second closest to 0, right? So it's not measured in terms of the number of edges, but in terms of the time it takes for the fire to reach. So we can make this systematic in the form of an algorithm, right? So for instance, we start at 0, and then after 10 units of time, we can see that vertex 1 is going to burn. And now at this point, this fire has started here, so it has reached up to some point, right? So this is not that there is no fire going towards 2, there is a fire, but it has only reached 1/8 of the distance because it has travelled 10 by 80 of the distance. Now after 6 more units, this fire will reach here, right? So there will be a fire going in both directions, but the fire will reach 2 before it reaches 4. So after 16 units of time from the beginning, that is 6 units of time after vertex 1 burnt, I have a fire which is kind of heading in this direction. I have this fire which has made some progress, but I have burnt vertex 2. Now I am at time 16, right? So if I continue for some time, then when I am 20 units away from this time, so at time 30, I will expect that vertex 4 will have burnt. Now at this point, there is a fire which has started from 2 towards 70, towards 3. There is this fire which is still running from 0 towards 2. Right? So there are these two ongoing fires which will eventually get there, but we may not need to, they may not need, for example, this fire certainly does not have any purpose to serve, because once it reaches 2, it's going to find that 2 is already burnt. So now proceeding after 30, the next thing that's going to happen is that I'm going to have 2 fires going in this direction. So after 5 units of time, something is going to happen, right? So at 35, node 6 will burn. At 45, node 10 will burn. And finally, the only unburnt vertex at this point is 3, and the only way it can burn is from 2. So since 2 burnt at 16 and it takes 70 units of time from 2 to reach 3, at time 86 I will finally see vertex 3 burn, right? So this is the way we want to track this process and compute these distances. So from this, what we will conclude is the shortest distance from say 0 to 3 is 86, from 0 to 5 is 45, and so on. So to make this actually effectively computable, we need to calculate these times and decide which will burn left, what we did by kind of examining the graph by hand. So we compute what is called an expected time to burn, right? So initially we know nothing about the graph, so all the vertices may never burn. So we can just assume them to be some arbitrary value infinity. So all vertices, as far as we know, will never burn, right? Now we set fire to the start vertex. So remember, this is a single source shortest path problem. So there will be a well-defined start vertex which we start at. So we know that at time 0, we will burn vertex 0. So that expected burn time of 0 gets updated from infinity to 0. But once we know when vertex 0 burns, we can look at its outgoing edges, right? And from these outgoing edges, we have a better estimate of when its neighbors will burn, right? So I know now that vertex 1 will burn not later than 10 and vertex 2 will burn not later than 80. So I can update their times from infinity to 80. Now I look at all these expected times and hopefully there is something which is finite, and among the finite ones, whichever one is smallest is the one that's going to burn next. So I can now see that there are only two finite ones, 80 and 10, but 10 is smaller than 80, so in 10 units of time vertex 1 will burn. And once vertex 1 burns, again I can look at its neighbors. So one of its neighbors is already burnt, so it's not useful to me, but neighbors which are not burnt, namely 2 and 4, I can update my estimate. So earlier I believed that vertex 2 would burn at time 80, but now I know that it's actually going to burn not later than 16 because the vertex, the one fire is going to reach it at time 16. Similarly, the vertex 4, which was earlier assumed to never burn, is now going to definitely burn within 30 time units. So I can update now those to 16 and 30. So at each point when I burn a vertex, I will update the expected time of its neighbors and I will keep then picking up the smallest unburned vertex to burn next. So after this, now I can see that I have two things which are unburnt and which have a finite time to burn. So of these, 2 at 16 is the earlier one, so I will burn that. This will update only one thing, namely the time at 3 from infinity to 86, because it was earlier believed to never burn. Now I know it will burn within 70 time units of 2 having burnt. So now I have these two which are unburnt, 86 and 30. So I pick the smaller one of these two and burn it. And now I have to look at the new things that I learned from that. So from this I learned that vertex 5 will burn at time 80 and vertex 6 will burn at time 35. Right? So now I have all my unburned vertices have a finite estimate. Right? So the smallest estimate among those is actually going to be the one that will burn next. So I burn at 35 vertex 6, and with this I get a new update saying this is not 80 but 45. Right? So now I am left with these two. So I burn the one at 45 and finally I burn the one at 86. So this algorithm that we have just described is a very well known algorithm due to a very famous computer scientist called Edgar Dijkstra. So this is often called Dijkstra's algorithm. So in Dijkstra's algorithm, we are choosing a strategy to burn vertices based on what we have seen now and what is the best at the next step, right? So we have made these estimates about when things are going to burn, and we are using these estimates to guide us to tell us which vertex burns next. So this kind of a short-sighted strategy where we are ignoring anything else, we are just saying, okay, so far this looks like the best thing to do next. We will not look 2 steps ahead, for example, right? We will just directly burn it and proceed. We never go back and make a choice that we had, take a choice we had taken before and undo it, right? So this kind of forward thinking strategy where we keep making a local decision and never go back on it is called a greedy strategy, okay? So greedy for the obvious reason, you have a number of choices given to you, you take the one that looks best and then you jump into it, right? And you never undo that. So whenever we have a greedy strategy, we have to argue that this short-sighted strategy of doing whatever looks good next is better than having to wait and do something later on. So very often this is something that happens, right? So you're looking for to buy something and you go to a shop, right? And in that particular shop there are 5 things on display which are of interest to you, and one of them is the best. Now if you had a greedy strategy, you would buy that. But if you were not greedy, then what you would say is, okay, there are 3 other shops which are selling similar things, maybe they have different products which might be more interesting. So you would say, okay, in this shop this is the best, but I am not going to immediately go for this, I am going to go to the other shop and check and so on, right? So then your strategy is less greedy, you are not looking at the very first option that comes your way. Whereas here in Dijkstra's algorithm we are doing that. So whenever you have a greedy strategy, you have to argue that it is correct. So each new shortest path extends an earlier one, right? And by induction we have found paths to all the vertices already burnt. So this is now the strategy that we have at some given point, right? So initially we burnt 0, so that's clearly the shortest path, right? And now when we burn one more vertex, what we are inductively assuming is that we have found the shortest path. This is our justification for the greedy strategy, that every time when we choose the minimum expected time to burn, it is actually the minimum time among all the vertices which is going to burn. So at any given point we have burnt everything, and whatever we have burnt has got the correct answer. Now we have to check why the extension is going to continue to give us the correct answer. Right? So supposing we choose to burn a vertex V which is connected to, so now it must be connected, the fire has to reach V. So let us assume the fire is going to reach V from X. Okay. What we have to argue is that the fire that reaches V from X, because right now we believe is the next one, is not going to be wrong, because later on there is a fire from some other vertex which comes indirectly, which should have arrived earlier. Right? So at the time when we decide to burn V, we should rule out the possibility that we can get this kind of a fire which is coming from, see, it cannot come directly from Y to V, because if it was from Y to V, I would have chosen Y instead of X to update the time of V. So there must be some indirect path which I don't know of now, which causes V to burn faster than if I burn it from X, and we have to say that this cannot happen. Well, okay, so now why can this not happen? Well, first of all, let me say that this is some M and this is some N. So the fact that I chose to burn V before W means that M must be smaller than N. Right? It cannot be bigger than N. Right? So N is at least as big as M, and now I have to come and do something here. So this has to be at least 0. Right? So I have N plus some Q. So I am comparing M to N plus Q, the two steps on the other direction. And Q is, and N is at least as big as M, and Q cannot be negative. So Q cannot reduce N, right? So this basically tells us that this going around these two things cannot be shorter than coming this way. Now if Q could be negative, right? If I have this and if Q is negative, then I have a problem, right? So supposing this is 5 and this is 7, but this is minus 3. Then by choosing 5 right now it looks good. But actually if I chose the 7, then it would allow me to come back and finish this move in 4, 7 minus 3. Right? So this is why we had assumed initially that there are no negative edges. So it's not a question of negative cycles, no negative edges at all. Only if we have no negative edges can we guarantee that this particular greedy rule of Dijkstra to pick the shortest vertex, shortest time to burn available to me right now as the next vertex to burn is correct. Right? So we cannot use Dijkstra's algorithm with negative edge weights, because this argument will not work anymore. So let's look at an implementation of this. Right? So we need to maintain two things. Right? We need to maintain this burning. Right? So burning is the same as visiting. So we need to keep track of which vertices have been burnt or visited, and we need to keep track of when a vertex is going to burn, which is basically the distance. Right? So distance or time is the cost, right? So we want to keep track of the visited status, true or false, and the distance. So initially we said that everything is going to be assumed to burn at infinity. It is not going to burn at all. So what is infinity, right? So we need a value for infinity, because we can't put infinity into our Python code. So one way of thinking of infinity is that something which is larger than any path that you could find. So we have a weighted graph. So there are some weights in our particular weighted graph matrix. So supposing I take the largest weight amongst these. Now the longest sequence of edges that connects two vertices in the path has at most n minus 1 edges. So if I take the longest weight, largest weight, and multiply it by the number of vertices, then this must be bigger than the length of any path which is actually there in the graph. Right? So this is what we are doing here. So initially we are finding out, so this is S is our source matrix, and W mat is the weighted adjacency matrix that we are working with, right? So now we take this weighted adjacency matrix and we use, as usual, the shape attribute to find out how many rows and columns there are. Remember, now this is going to be, we are going to assume this is actually a two-dimensional matrix. So the 0th entry, so this x here, x is 0 and x is 1. So this will be the edge information and this will be the weight information, right? So ij0 will be whether there is an edge from I to j, ij1 will be what is the weight of the edge from I to j, and ij1 will be non-zero only if there is an edge. So if there is no edge, there will be no weight. Right. So we get the shape, so we get the rows and columns. So now from this we make a crude estimate of infinity, right? So we say take the maximum value that appears anywhere in this weighted matrix, right, multiplied by the number of rows. This is the length of the longest path you can get by having the largest weight repeated again and again, and then just for good measure throw +1. So, this is a very conservative estimate, but it is certainly larger than any real path distance that you will find. Right? That is all we want. Infinity should be such that if I compare it to a real path, infinity must be bigger. Okay, so now I have set my, so I have this visited dictionary and the distance dictionary, and for every vertex initially I set visited to false and I set distance to infinity, right. So, this is my initialization, that is what I have done so far. Now I am ready to get started. Right. So, the way I get started is by saying let me set the distance of the source vertex to be 0, but I have not yet visited it because I am going to put that into this loop. So, what I will typically do is I will look for the smallest distance vertex which is not visited, right. That is what I will look for, that is my strategy, right. I look for the expected burn time of the unburnt vertices which is smallest. So, in our current terminology, that is the distance to vertices among the unvisited vertices, that is the smallest. So, at the moment everything was infinity and I set distance s to 0, but I did not set it to be visited. So, the first vertex I am going to explore is in fact 0, but formally I will do it in a loop. So, what I will do is I will first find out, right, what are all the minimum distances that are there. So, I will take this min function, I will compute the distance for every vertex in my graph which is not visited, and I will take the minimum of these. Now, there could be multiple such vertices, right. At the beginning there will be only one, but at a given point there could be multiple such vertices. So, I will say that the next distance that I am going to explore, next d is the next distance, is the minimum distance among the unburnt vertices. Now, I have to find the vertex for which that is the minimum distance. So, that is my next thing. I will say the next vertex list is a list of all vertices which are not visited and which have this actual distance, right. So, this is the 2 passes on the list. So, you can do it in an explicit loop, but I felt that this was the fastest way to do it. So, you first scan it once to find what is the minimum distance among the unvisited vertices, then you scan it a second time to find out which are all the unvisited vertices which have that distance, right, and that is my next V list. Now, it is conceivable that there are some vertices which are never going to be visited, right. So, basically if I do not have any vertices in this list, I will just get out and I will not continue. So, this is just a kind of to handle a boundary condition, right. So, now the real situation is going to happen when I find these things. So, I need to now choose one. So, I choose the smallest vertex among the minimum vertex list to be the one to burn next. So, these are all vertices which have the minimum distance and are unvisited. So, I pick one of them and I make them visited and I will call that next V. So, how do I visit it? I will first set its value to be true, and then I have to take all its outgoing. So, I have next V here, which I am going to, and then I look at all its outgoing edges and I will update for all these vertices the time that they burn, which is their distance, to be the minimum of their known time. I already know they are supposed to burn at some point, or the time I will get if I burn it through next V, right. So, I take the minimum of the existing distance of V and the distance from the new vertex next V plus the edge weight. So, the edge weight, remember, is I j comma 1, right. So, this is just saying that for each vertex update its distance to be either the current distance or the distance from the vertex I just burnt plus 1. And now I kind of come back and do this again, right. So, this is my implementation, right. So, I set the distance s to 0 and I repeat until all the reachable vertices are visited, find the next vertex V to visit, set it to true and recompute the distance for every neighbor. So, this is with an adjacency matrix, and as you might guess, this is not likely to be ideal in terms of computational complexity. So, this itself requires n squared time, because I have to go through this entire weighted matrix, find the maximum value, that is an n squared size matrix, and then add something to it, right. Now, this main loop runs n times, because in every iteration of the loop I find one more shortest distance, right. So, I keep enumerating these vertices one by one. So, I need order n time to find the next vertex to visit, and I need order n time, so that is this part, right. I need to scan through the entire thing to find the minimum distance and then scan through it again to find which vertex has the minimum distance. And then I need order n time because I have an adjacency matrix. I need order n time to update these distances. I have got to go through all the columns in my matrix, and wherever a vertex is not visited, I have to check its distance and update it. And regardless of the degree of this vertex, I have to go through all the columns, right. So, I have an order n outside and I have these 2 order n steps inside. So, this is going to be order n squared. So, the usual thing is what happens if we move to an adjacency list, right. So, here is the same thing with an adjacency list. So, now I am passing a weighted adjacency list which I will call W list. So, again I will compute infinity in a similar way. I mean, so basically I take the length, this is the number of vertices, the length of the number of keys of my weighted adjacency list, and multiply it by the maximum value of all the weights in my adjacency list. So, every entry in my adjacency list is of the form v comma d. So, u2 v with distance d. So, I take the maximum among these d's and multiply it by number of vertices, add 1. So, this is the same infinity as the earlier one, except that I am doing this in order m time, right. Why am I doing it in order m time? Because this process of finding the maximum across all the adjacency lists is proportional to the number of all the edges in my adjacency list. So, it is not order n squared, but order m. So, that is a good piece. I have done one thing which was order n squared before, I have replaced by something which is order n. So, that is good. Now, the rest is similar, right. I kind of initialize the visited and distance to empty, then I update these things, and then I start with distance s is 0. So far so good. Now, again I have this outer loop which is order n. In this outer loop we had 2 nested things which are problematic. One is solved, because now if I want to update the degrees, this is order m. Right? Because once I get a vertex and I want to update all its neighbors, I only have to go proportional to the degree of that vertex, which amortized as usual across all of them is going to be the sum of the degrees, which will be proportional to the number of edges. But the problem is that this remains. The problem of identifying the minimum vertex remains, right. I need to find the minimum vertex which is there, and therefore, I need to spend order n time to scan through all the vertices which are unvisited and find the minimum, right, because these are in no particular order. So, if we do not have a better way of doing that, even with an adjacency list, the second loop is going to take order n squared time. So, we will see later that there is actually, this is therefore a useful thing to be able to do, to take a collection of values and to be able to extract the minimum, right. If it is sorted, of course, I can extract the minimum, but if it is not sorted, we can still do something clever and extract the minimum fast, and that is what we will need to do. But till we have that, we are stuck with this problem that Dijkstra's algorithm takes order n squared time, whether you use an adjacency matrix or a list, right. So, Dijkstra's algorithm basically computes single source shortest paths when we do not have negative edges. It uses a greedy strategy to identify which vertex to visit next, mainly picks up the vertex with the expected burning time which is minimum among those which are unburnt, or unvisited vertex with the smallest distance. And whenever we use such a greedy strategy where we are ignoring everything and we are not looking multiple steps ahead but choosing the optimum one right now, we have to justify why it is true. And we proved that if the edges indeed have non-negative weights, then you can argue that you will not find a later path which will become shorter than the path that you have just found. So, in that sense, Dijkstra's algorithm is correct without, if you assume that there are no negative edge weights. But one of the bottlenecks is that because of this problem of having to identify the next vertex as the one with the minimum distance among the unvisited ones, that takes order n time inside an order n loop. So, we have this complexity bottleneck of order n squared whether we use adjacency matrix or we use an adjacency list.